Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Upstage Solar Open, a 102B bilingual Mo model for underserved languages. Solar Open is a 102 billion parameter bilingual mixture of experts language model designed by Upstage. It's built to serve Korean and English, with a special focus on high-quality Korean capabilities and strong reasoning. The team trained it on 20 trillion tokens, including 4.5 trillion tokens of synthetic data, and they're releasing it as an open-weight model. More than just a single model, Solar Open is meant to be a blueprint for how to build frontier-level systems for languages that don't have much data. The motivation behind Solar Open starts from a simple imbalance. Most open large language models are optimized for English and increasingly for Chinese. Korean, by contrast, makes up less than 1% of the indexed web, and there are very few large, high-quality Korean datasets or frontier-scale open models. When we simply throw Korean into a generic multilingual model, performance on real Korean tasks suffers. The tokenization is inefficient, cultural context is missing, and downstream accuracy lags far behind English and Chinese. The authors frame their work around three tightly connected challenges. First, Korean data is scarce and noisy compared to English, so they can't just scrape more web text and hope for the best. Second, they need to optimize the model bilingually, balancing Korean and English across training stages instead of treating Korean as an afterthought. Third, they want strong reasoning, which requires reinforcement learning at scale, not just supervised fine-tuning. And finally, they need all of this to be operationally scalable. Data generation, curriculum, and RL must work together without collapsing under engineering complexity. At a high level, Solar Open is a sparse mixture of experts transformer. It has about 102.6 billion total parameters, but only 12 billion are active for any given token, thanks to a top 8 of 128 expert routing scheme plus one shared expert. The model is explicitly bilingual, targeting Korean and English, and supports very long contexts up to 131,000 tokens. Under the hood, it uses a custom tokenizer and a carefully tuned MoE architecture to balance efficiency, stability, and linguistic coverage. The paper's main contributions fall into four buckets. First, they aggressively generate 4.5 trillion tokens of synthetic data to overcome Korean data scarcity and to feed reasoning and RL. Second, they design a bilingual, reasoning-aware curriculum that schedules 20 trillion tokens across phases, gradually increasing quality and synthetic ratios. Third, they introduce SnapPO, a decoupled reinforcement learning framework that makes multi-objective training, like reasoning, safety, and preference alignment, scalable and manageable. And finally, they position Solar Open as a general methodology for underserved languages with Korean as a concrete case study. In terms of performance, Solar Open is particularly strong where it was designed to be strong. Korean domain expertise. It leads comparable open models on Korean finance, law, and medical benchmarks. Its general knowledge performance is competitive in both Korean and English, and its preference alignment scores are high in both languages. For mathematical reasoning, it's solid, but not at the level of specialized math-focused models, which reflects a deliberate trade-off in the data design toward natural text and domain expertise. Tokenization is a big deal for Korean. Many global tokenizers fall back to byte-level encoding on Korean text, which inflates sequence length and breaks meaningful units. Solar Open uses a custom byte-level BPE tokenizer with a large vocabulary of about 196,000 tokens, trained on data that deliberately oversamples Korean and key domains. It splits digits into individual tokens to stabilize arithmetic and preserves whitespace patterns, which is crucial for code. Evaluations show that this tokenizer achieves better compression on Korean than many global models, which directly improves training throughput, inference speed, and effective context length. The team doesn't just look at tokenization on raw web text. They also measure efficiency on actual model-style outputs, bilingual instruction following responses, with and without explicit reasoning. On these conversational traces, Solar Open's tokenizer is particularly efficient for Korean, including when the model produces long chains of thought. It also remains competitive on English. Fewer bytes per token and fewer tokens per answer translate directly into faster and cheaper inference in real-world deployments. Architecturally, Solar Open is a sparse MoE transformer with 48 layers and a hidden size of 4096, using the SILU activation function. There are 129 experts in total, 128 routed experts, plus one shared expert that acts as a safety net when routing is uncertain. For each token, the router selects the top 8 experts. Unlike some other MoE models, SolarOpen uses MoE layers throughout, with no initial dense layers. To keep training stable and avoid expert collapse, they combine expert bias with a sequence-wise load balancing loss, tuned through ablations on a smaller prototype. For pre-training, SolarOpen sees about 19.7 trillion tokens. This includes large English general text, math and code, Korean general text, Japanese, other multilingual data, and carefully curated domain-specific corpora in finance, law, and medicine. On top of that, they generate 4.5 trillion tokens of synthetic data using SolarPro 2 and other permissive open models. After pre-training, there's a mid-training stage with another 1.15 trillion tokens focused on reasoning, long context, and preventing forgetting. The data isn't just dumped into the model, it's fed through a curriculum. Phase 1 starts broad and relatively noisy, with a low synthetic ratio, to maximize coverage. Phase 2 is split into 3 subphases where both the quality thresholds and the synthetic fraction increase, eventually keeping only the top slice of educationally valuable content. Phase 3 then specializes on Korean cultural knowledge, advanced math, and repository-level code. Throughout, they apply 3 layers of filtering: a general quality classifier, an educational quality scorer, inspired by FineWeb-Edu, and embedding-based topic clustering to keep important domains well covered. Training on nearly 20 trillion tokens with a 100 billion parameter MoE model is an engineering challenge. The team runs on a 60-node NVIDIA B200 cluster and pushes throughput up to about 7,200 tokens per second. They move from DeepSpeed to Torch Titan, using fully sharded data parallelism and a hybrid sharding scheme to scale across nodes. They optimize MoE kernels, fix subtle D-type issues in the router, and add fast paths when expert parallelism isn't used. On the data side, they exploit the structure of Arrow datasets, so each worker only loads its own shard, cutting initialization time from hours to minutes. To test whether their curriculum and synthetic data strategy actually help, the authors compare SolarOpen's training trajectory to GLM 4.5 base, a similar scale model trained on 23 trillion tokens. On English benchmarks like MMLU, MMLU Pro, and HelloSwag, SolarOpen reaches GLM's performance at around 10.7 trillion tokens. On Korean versions of those benchmarks, it matches GLM at about 17.8 trillion tokens. That's only 48% and 77% of GLM's total token budget, respectively, suggesting that a well-designed bilingual curriculum plus targeted synthetic data can significantly improve training efficiency. Between pre-training and post-training, there's a mid-training stage that still uses next token prediction, but on more specialized data. Here, the focus is on reasoning and long context understanding. They generate about 850 billion tokens of reasoning trajectories, which is 64% of the mid-training data. For each challenging query, they synthesize 2 to 5 different solution approaches and package them as coherent documents. This gives the model a rich library of atomic reasoning steps and alternative paths, which later RL can recombine. Around 80% of this mid-training data is synthetic, and Korean and English are kept roughly balanced. After mid-training, the model goes through supervised fine-tuning. Here, the goal is to show the model complete, successful reasoning trajectories and high-quality answers. This stage teaches the model how to follow instructions, how to use the chat template, and how to present reasoning clearly. Importantly, they also feed back successful trajectories discovered in early RL experiments, creating a loop where RL discoveries improve the supervised data. Conceptually, SFT is where the model really learns atomic reasoning skills that RL will later compose and optimize. Not all questions are equally useful for training. To focus on the right ones, the team builds a difficulty estimator. The idea is simple. If several strong models give consistent answers, the question is probably easy. If they disagree, it's likely hard. They collect responses from multiple models, label pairwise difficulty with an LLM, and train a classifier. This estimator is then used to filter out trivial queries, to apply stricter checks on very hard ones, and to balance the difficulty distribution in SFT. The same signal later helps choose RL prompts and shape rewards. To get enough challenging questions, the authors don't just rely on existing datasets. They fine-tune SolarPro 2 to act as a query generator. Given seed texts, it produces new, semantically related questions. At first, the generator tends to produce easy, shallow queries. To fix this, they use the difficulty classifier to score generated questions, then iteratively retrain the generator to favor harder ones. This cyclic process gradually shifts the distribution toward more demanding, reasoning-heavy queries across domains like math, code, science, and medicine. SolarOpen is also trained to act as an agent that can use tools. To do this, the team builds two simulation pipelines. The task-oriented simulator creates complex tasks that require multi-step tool use with explicit success criteria. The user-oriented simulator models realistic conversations where a user gradually refines their request over multiple turns. They synthesize tool specifications and API graph, then generate trajectories that include planning, tool selection, argument construction, and error handling. Training on this simulated data alone yields around 60 points on the Tau2 agent benchmark, even before dedicated RL for agents. To go beyond surface-level Korean, the authors build specialized datasets that capture deeper cultural and historical knowledge. Using embeddings, they link related Korean documents and create multi-hop question-answer pairs, comparative questions, causal chains, multi-document reasoning, and theme inference. These are used throughout post-training, SFT, preference optimization, and RL, to teach the model to reason over Korean sources, not just recall isolated facts. For sensitive topics, they train reward models that encourage nuanced, culturally appropriate responses. Safety is handled through a fairly detailed framework spanning 38 risk categories, including child safety, weapons, privacy, misinformation, political manipulation, and more. The model is trained to either refuse and redirect, explaining risks and pointing to safer topics, or to provide a bounded, supportive answer, which they call safe completion. Self-harm is a good example. Instead of a blunt refusal, the model is trained to respond empathetically and point to professional resources. To avoid over-refusal, they also include adversarial examples where the query looks dangerous, but is actually educational or benign, and they train the model to answer those appropriately. For reinforcement learning, the team introduces SnapPO, which stands for Snapshot Sampling for Policy Optimization. The key idea is to decouple three steps that are often tightly coupled: generating responses, computing rewards, and updating the model. They use VLLM to generate multiple responses per prompt and cache both the text and the behavior policy's log probabilities. Then, in a separate offline step, they compute rewards, using correctness checks, reward models, or pattern detectors, per domain, and cache those too. Finally, they train the policy using group sequence policy optimization on this cached dataset, leveraging the same Torch Titan infrastructure. This separation makes it much easier to scale and to experiment with new reward functions or data mixes. Decoupling RL into 3 stages has practical benefits. Because generation and training don't compete for the same GPUs, you can scale each side independently and get close to linear speedups when you add hardware. You can also assign different hardware types to generation and training if that's more efficient. Since responses and rewards are cached, you can flexibly mix data from math, code, safety, agents, and Korean culture without regenerating everything. And if you want to tweak a reward function, you can recompute rewards on existing responses instead of rerunning the whole RL loop. The first RL phase is all about reasoning. The team trains on roughly 200,000 prompts that emphasize challenging STEM problems, code generation, and agent workflows. For math and science, they use verifiable rewards based on correctness and sometimes process quality. For code, they rely on execution-based rewards and style or efficiency checks. For agent scenarios, they combine task completion, interaction quality, and error recovery into composite rewards. The difficulty estimator helps them focus on prompts where exploration is most valuable, rather than wasting RL budget on trivial questions. The second RL phase shifts from pure reasoning to human preference and safety alignment, using a cyclic DPO setup. Here, the model learns from preference pairs that cover explanations, writing quality, and conversational style. It also sees safety scenarios across the 38 risk categories, plus examples of degenerative behavior like repetition or formatting issues. There's targeted data for Korean cultural sensitivity and for teaching the model to self-correct in agentic workflows. To avoid losing the reasoning gains from Phase A, they keep a slice of reasoning data in the mix, using KL-style regularization in the DPO loss to stabilize behavior. On Korean benchmarks, SolarOpen performs very well. It either matches or surpasses GPT-OS 120B High on most general knowledge suites like KMMLU and KMMLU Pro, and on cultural and reading benchmarks like CLIC and HARAE. In domain-specific tests, it leads by about 3 percentage points in finance, nearly 3 points in law, and over 8 points in medical QA, compared to GPT-OS High. Preference alignment is also strong, with a top score on CoArena Hard v2. For math, it's competitive on CoAIM and HRM8K, though not at the level of models that are heavily optimized for math alone. In English, Solr Open holds its own against comparable open models. On MMLU and MMLU Pro, it's competitive with GPT-OSF 120B Medium. Its math performance is particularly strong on AIM 2024 and 2025, and on HMMT 2025, often beating GPT-OSS Medium. For code, it scores well on Live Codebench v6, though it trails GPT-OSS Medium, which is more code-focused. On preference benchmarks like Arena Hard v2 and Writing Bench, Solr Open shows strong alignment, indicating that the RL and DPO phases are effective beyond Korean. The authors are clear about limitations. First, while math performance is good, it doesn't match specialized math reasoners because the data mix prioritized natural text and domain expertise. Second, the methodology has only been fully tested on Korean, which is low resource but not extremely low resource. It's unclear how well this approach scales to languages with far less text. Third, the curriculum depends on machine-learned filters for quality and topic selection, which adds complexity and bakes in certain assumptions. And finally, the usual RL challenges remain: designing robust rewards, ensuring good exploration, and maintaining alignment under distribution shifts. Beyond the specific numbers, Solr Open is meant as a template. It shows one way to build a strong model for an underserved language by combining synthetic data, bilingual curricula, and scalable RL. The authors argue that we now need principled language scaling laws. How does adding a new language affect performance on existing ones under fixed budgets? They also highlight continual training plus tokenizer expansion as a promising path for adding languages to existing models, rather than always training from scratch. And they suggest that future work should aim for simpler, more assumption-free data curricula that are easier for smaller communities to adopt. To wrap up, Solr Open demonstrates that aggressive but carefully targeted synthetic data can meaningfully offset language scarcity. A bilingual curriculum that explicitly tracks quality, domains, and reasoning can make training more efficient than just scaling tokens. Decoupled RL frameworks like SnapPO make it feasible to optimize for multiple objectives: reasoning, safety, preferences, and culture at scale. And in practice, Solr Open delivers strong Korean capabilities and competitive English performance, setting a new open baseline for Korean and offering a roadmap for other underserved languages.